Welcome to BreadCrumb Basics. We're going to talk about our BreadCrumb models. We're going to be talking about our LX5, our ME4, our JR3, our DX2, our ES1, our KM3, and the slipstream. Also in this course, we'll be defining meshing as Rajant does it. We'll also delve a little bit into layer 2 networking. And at the end, we'll talk a little bit about our administration software, BC Commander. Our first model, the LX5, is good for mining, military, transportation, and primarily infrastructure. The enclosure can house up to 4 radios, and those radios can come in any number of different frequencies: 5 gigahertz, 4.9, 2.4, and 900 megahertz. This model has a power consumption of nominally about 8 watts at 24 volts. Its max draw will be 33 watts at 24 volts DC. For a 3 radio model, it'll be 7 watts nominally with 26 watts maximum at 24 volts DC. This model has dual quad-core processors. It's designed to IP67. It's rock solid in its construction. It has security capabilities for military applications to include Suite B and FIPS 140-2. There are several different models of the LX5. You'll find a table of the models on the slide before you. This model can house up to 4 radios, as I stated before. This can include any number of MIMO radios, so we can have 3 MIMO radios, so 3 2x2 MIMO radios, or we can have a combination of MIMO and SISO radios. The next model we'll talk about is the ME4. The ME4 is kind of the workhorse of our fleet. This enclosure has 2 radios and up to 4 antenna ports. The radios can, again, be any combination of 5 gigahertz, 4.9, 2.4, and 900 megahertz. The power consumption for this radio is maximum up to 19 watts at 24 volts DC. This is, again, a very rugged IP67 unit. It can be out in the elements with no problems at all. This unit is designed for mining, ports, transportation, oil and gas. This is a perfect unit for installation on mobile units because it has up to 4 antenna ports. Our next model is our JR3. The JR3 is a single radio unit. It is software programmable, so it can be either a 2.4 or a 5.8 radio. 1 single antenna, 1 single radio, and again, you have all of the limitations of a single radio. This unit is designed to be outside when properly weatherproofed. This unit is designed to also be an edge device. It's not designed to be an integral part of a mesh. You would install this on possibly a light duty vehicle that's not going to be part of the mesh for an extended period of time. You could put this on a pump. You could put this on a PLC. Again, an edge device, not necessarily meant to be infrastructure or an integral part of the mesh.
Our next model is the DX2. The DX2 is also a single radio unit. It's our lightest and smallest breadcrumb. It's made out of 100% magnesium and weighs only 123 grams. It's a single transceiver with a MIMO antenna system. This is frequently used in private wireless networks found on land, air, and sea, as well as autonomous vehicles. This model is perfect for drone deployments, as well as most small autonomy projects. The DX2 is fully compatible with all the other breadcrumbs in the Rajant product portfolio.
Our next model is the ES1 5250. This unit is a 2.4 and a 5.8 radio. It has a plastic case, but it is IP67 for moisture and dust. The caveat here is it is a plastic case, so when introduced into environments with vast temperature swings, the case could become compromised over time. This unit is a low-cost, mid-tier level unit, perfect for an oil and gas, transportation, and mobile units. I would suggest, however, if going to be introduced into rugged environments with vast temperature swings or long degrees of exposure to direct sunlight, probably best to put this in an enclosure of some kind. He's going to draw about 2 watts average and 15 watts peak at 24 volts DC. The next model is our KM3. The KM3 comes in either a 2450R model or a 2409 model. This is a non-ruggedized version of our ME4 BreadCrumb. It's intended for deployment inside a pre-existing outdoor NEMA enclosure. It has all the same characteristics as an ME4, all the same performance capabilities of an ME4, just without the IP67 housing. The KM3 BreadCrumb is an ideal wireless network solution for the energy market, particularly oil and gas operations that rely heavily on SCADA operations. Anytime you're doing SCADA, real-time monitoring, or video surveillance, and you have a NEMA enclosure to mount this guy in, he's got several mounting options to include DIN rail. Our next model is going to be the Slipstream. Now, the Slipstream is a BreadCrumb with no radios. Later in the course, we'll be talking about a protocol that Rajant uses called automatic protocol tunneling. This is a method that BreadCrumbs use to mesh over the wire in the same broadcast domain. The Slipstream was designed to be our APT, or automatic protocol tunneling master. His responsibility is to do all of the encapsulation and decapsulation of all Instamesh packets on the wire. In the past, networks that required large-scale bandwidth coming back to a central router met some kind of a bottleneck using a regular BreadCrumb as the APT master. With the Slipstream, there's no such bottleneck. The Slipstream allows for much faster processing and a higher level of bandwidth, to include aggregate bandwidth from all of our APT slaves. The powerful CPU is dedicated to kinetic mesh encapsulation and decapsulation. It is a seamless integration with current BreadCrumb models. When you see it on BC Commander, you'll notice that you program him just like a BreadCrumb, he just doesn't have any radios. The Slipstream is designed to be indoors, to be in the server room and connected directly to your router. This supports several strong cryptographic options as well. In the past, when using a BreadCrumb as your APT master, you were limited to about 87 megabits aggregate on the wire. With the Slipstream, you're now capable of up to 605 megabits. Even with encryption, AES 256, we're capable of up to 189 megabits per second. BreadCrumbs are intelligent network nodes that perform multiple functions. They act as a switch. They actually make routing decisions. They're capable of multiple VLANs. BreadCrumbs can also be gateways. That is, they can NAT, perform network address translation from IP space to IP space. They can also be a network bridge, and all of them have full access point functionality. As a switch, they constantly scan all the mesh network connections across all frequencies. They select the best connection for each node and for each peer, and they send packets down those connections. BreadCrumbs make layer 2 routing decisions. So each node deployed on either infrastructure or mobile nodes are capable of making packet by packet routing decisions. Instamesh, Rajant's proprietary networking protocol, allows BreadCrumbs to make routing decisions on the fly, moving packets between interfaces to find the best and fastest route. BreadCrumbs are all 802.1q compatible. They're all capable of supporting VLAN trunking. All BreadCrumbs, with the exception of the JR3, are capable of network gateway functionality. That is, they would be able to take a packet from one IP space and translate that into another IP space. So you could go from a 10 space to a public IP space of 192.168. They're also capable of being network bridges. That is, you can just bridge your wired network to your wireless network. Each breadcrumb is also capable of being an access point. That is, they can allow 802.11 clients to access the network wirelessly. Each breadcrumb has up to 4 virtual ESSIDs per radio interface. So an ME4 with 2 radios could have up to 8 virtual ESSIDs. Each one of those ESSIDs with its own unique security and its own unique native VLAN. BreadCrumb architecture consists of up to 4 radios. Inside, we have our InstaMesh proprietary networking protocol. InstaMesh is what makes Rajant meshing possible. InstaMesh is responsible for making sure those radios move packets from point A to point B down the fastest route. We use a protocol we call costing. A mesh network is a collection of wireless network devices, 3 or more, that associate to each other in order to form a path for data to flow. 2 devices does not a mesh make. 2 devices is a point-to-point. So as 2 breadcrumbs turn on, they are automatically configured to mesh with each other out of the box. InstaMesh protocol allows the breadcrumbs to find each other and to mesh automatically with no interaction. They will join on a 2.4, a 5.8, and a 900. This will allow them to make a multi-frequency peer-to-peer connection. So now we're moving packets down all 3 frequencies. When we turn on a third, he introduces himself into the network, and as more of them turn on, they associate, and now we have a full peer-to-peer mesh network with no single controller. Now, once all of these nodes come on, they find each other, we now have a layer 2 network formed. We can now connect an 802 wireless client, or we can connect via Ethernet. So now these 2 machines can find each other. Again, remember, this is layer 2. So the breadcrumbs can have one set of IP addresses. The laptops could have a separate IP address. So for instance, the breadcrumbs could be in the 10 space, 10.x.y.z, whereas the laptops could have a 192.168 address. This is all layer 2. IP addresses don't matter. With this mesh, our packets have multiple paths. We don't have to define routes with a Rajant network. The breadcrumbs do it for us, and they do it based on route costs. A route cost is Rajant's most realistic and fastest metric to grade a peer connection. A route cost is most closely defined as the amount of time it takes to successfully deliver a packet in microseconds. That is a packet sent and an acknowledgement received. As we have localized interference, because we have multiple frequencies available to us in our enclosures, depending on what frequency that interference is, we will be able to route around or even through that interference because of our costing algorithm. As the interference comes into play, the cost will start to go up because it takes longer for those packets to successfully be delivered. As route costs go up, InstaMesh allows the breadcrumbs to make on-the-fly routing decisions. So as the costs go up, they can find different paths to route packets. In this instance, we have 2.4 gigahertz interference. So as packets are moving from the source to the destination, we can either route around or even route through. The way the route costs work: from the moment a packet leaves to its destination and an acknowledgement packet is received, the clock stops. We know that this is a good cost. In the case of localized interference, the breadcrumb will send the packet, but because there's localized interference, no reply is sent. It's not until the acknowledgement packet is received that the clock stops. We now know that this particular route has a high cost and most likely will not be used. A Rajant mesh network is very resilient to the loss of breadcrumbs. That is, when we lose a breadcrumb out of a network, the packets still have many options to go. In a properly designed Rajant network, each node has at least 2 different connections on 2 different interfaces to 2 other nodes in the network. So in the event of this particular scenario where we lose a breadcrumb, the route cost to that breadcrumb will go up very rapidly. The breadcrumbs will find alternate routes. Instamesh will get packets from the source to the destination very rapidly. Any breadcrumb on the network can be connected to the LAN. Multiple breadcrumbs can be connected to the LAN in the same broadcast domain. This is what we call automatic protocol tunneling. This allows for the breadcrumb network to have no single point of failure. Packets going to the LAN and going to the application servers are never interrupted. This allows multiple ingress points into the wired network. And again, this eliminates a single point of failure. Adding breadcrumbs to a network only makes the network stronger. Instamesh allows breadcrumbs to scale. The more breadcrumbs, the more options for packets to be routed. 4 things that breadcrumbs must share to mesh. They must share at least 1 radio channel. They must share a network name. They must share a network key and any crypto settings that you've employed. In a traditional Wi-Fi based mesh, typically you have 1 radio that's dedicated to backhaul and 1 radio that's dedicated to servicing Wi-Fi clients. So you have 1 half duplex device that's servicing a bunch of other Wi-Fi half duplex devices, and then a half duplex device that's performing the backhaul with an Ethernet bridge in between. This is how you lose bandwidth for multiple hops. These radios can transmit or receive, but not at the same time. So in this case, we have a traditional Wi-Fi based mesh network. We have access points servicing multiple clients. If one of these nodes goes out, all of those clients are completely starved for information, and they're not able to talk to each other, and they're not able to talk back to the application server. In a Rajant mesh network, all peers are connected. If we lose one of the access points, it doesn't matter because the peers can still talk to each other and they can make routing decisions. Breadcrumbs can talk on multiple different frequency interfaces. Rajant can pass packets seamlessly between those interfaces. You have an infrastructure node in this case that's talking on 5 gig and mobile units that are talking on 2.4. Okay, you've heard me talk about IP addresses. What are IP addresses? An IP address is a unique string of numbers separated by periods that identify each computer using internet protocol to communicate over a network. Why do I need an IP address? Well, an IP address serves a couple of primary functions. It identifies a unique interface on a network, and it provides a physical address, much like your home or your business. A packet needs to know how to find a home. Now, you've heard me talk about layer 2. Breadcrumbs don't use IP addresses to route. However, the application layer, say your PLC or your video camera, they need an IP address to function on a network. Each packet needs to know where to find a home. There are 2 types of IP addresses that you might find in a network. An example of that would be, say, your public IP address, a 192.168.x.y. Then you also have an external IP address. This is what the internet sees. An example of that might be 216.168.x.y. So when we talk about TCP/IP, the other thing we need to talk about is subnet masks. So what is a subnet mask? Well, a subnet is a logical subdivision of an IP network. The practice of dividing a network into 2 or more networks is called subnetting. This is the number of devices that will be on a particular network. An example of a subnet would be a 255.255.255.0. The 0 signifies the number of devices on that particular network, anywhere between 0 and 255. More specifically, the 0, the 1, and the 255 are usually reserved for specialized purposes. One of the things we need to focus on when we talk about layer 2 is the media access control address, or MAC address. Now, this is a unique identifier assigned to each network interface by the manufacturer. This is not something that changes or shouldn't change. And each physical hardware device should have its own unique MAC address. In your laptop, you have a few MAC addresses. You have a MAC address for your Ethernet port. You also have a MAC address for your wireless interface. What happens when you turn on a device and it tries to connect to a network? One of the first things to happen is something called an address resolution protocol, or an ARP. Basically, this is your device going out and trying to find out who they can talk to. They'll say, I have a message for this device. Where could he possibly be? So he sends out an ARP to find out where he is. All systems and all computers have the ability to reply to an ARP. They will reply to an ARP by looking up in their table as to whether or not they've ever seen this device before, and they will reply with an IP address. So, in this case, I have a message for device B. Where is he? Well, device B will reply, I'm at this location and here is my IP address. So each router, each switch keeps a record of each of these ARP replies, so that each time a device ARPs for a specific device on the network, the switch will have a record of where that device is physically located. And by physically, I mean which interface. So, breadcrumbs do something similar when they're looking for a particular breadcrumb or a particular route. They'll send out what's called a discovery ARP. Each breadcrumb device turns on and announces himself to the network. He sends out a series of discovery ARPs on all of his interfaces. Each breadcrumb knows to look for those ARPs and replies to them. So as the breadcrumbs find each other, they put themselves into their own breadcrumb tables, and they'll have a record of where they are, which interfaces they've spoken to each other on, and then when they need to communicate with those nodes, they'll know which interfaces to best communicate with those breadcrumbs on. Breadcrumbs, again, only need to share a few things in order to talk to one another, because, again, they operate at layer 2. All they need is a network name, a network key, one shared radio channel, and whatever security protocols you put in place in the form of packet cipher or per hop authentication. In order to manage your breadcrumb network, Rajant has BC Commander. This is our network management software. This is a Java-based application that allows the network administrator to manage a breadcrumb network. The computer running BC Commander needs to be on the same IP network as the breadcrumbs in order for BC Commander to manage your breadcrumb network. The administrator can utilize a couple of different views in BC Commander. We have a topology view and a table view. In the topology view, you can also utilize a map view. If breadcrumbs know where they are with the GPS receiver, you can overlay a map and actually see the breadcrumbs in accordance to where they are located on the map. The table view allows the administrator to see the network in the form of a spreadsheet. You can sort by name, you can sort by model number, you can sort by any one of your column headings, whichever might be useful to the administrator. So in summary, we've talked about the breadcrumb models, we've defined meshing, we've talked a little bit about networking, layer 3 and layer 2, and I've introduced you to BC Commander. There will be a short quiz at the end of this module. Good luck.